We were talking about graphing rational functions, and we want to be able to graph functions in different forms. So in this case, when we're referring to m and n, m is the degree of the numerator and n is the degree of the denominator. So there's three different forms that we want to look at: when m is less than n, when m is equal to n, and when m is greater than n. Then we can look at a rational function, an equation in the form r of x is equal to p of x divided by q of x. So basically what this means over here on the right, it just means that there's a function divided by another function. And it says that this is the highest degree m, and this is the highest degree n. The x-intercepts are where p of x is equal to 0. So this just says, when is the numerator equal to 0? That's where the zeros are going to happen. The graph has a vertical asymptote whenever q of x is equal to 0. So q of x, if this is equal to 0 in the denominator, then this whole function r of x will be undefined, and so we'll have a vertical asymptote. The graph has at most one horizontal asymptote, which is defined by the degrees m and n of p of x and q of x. And we'll take a look at that. So the horizontal asymptote. If m is less than n, if it's bigger on the bottom, then it's 0. So the horizontal asymptote will be y equals 0. Here in the numerator, we have the degree 0. In the denominator, we have degree 2. So it's bigger in the denominator, so y is equal to 0. If m is greater than n, meaning it's bigger in the numerator, there'll be a slant or oblique asymptote. So here we have the degree 2. In the denominator, we have degree 1. So there's no horizontal asymptote. Now we have to be ready for polynomial division. If m is equal to n, if it has the same degree on the top as on the bottom, then the answer is a over b. So here we have highest degree 2. In the denominator, we have highest degree 2. So the horizontal asymptote is y equals a divided by b. We also are going to have to examine continuity. A function that is continuous can be drawn without lifting your pencil. Breaks in the continuity are asymptotes or point discontinuity. Point discontinuity or holes, if the original function is undefined for x equals a, but the simplified rational expression is defined for x equals a, then there is a hole at x equals a. So we're going to take a look at this example here. There's the steps to find the hole. So step 1, factor the numerator and the denominator fully. So here we have example f of x. We have 3x minus 9 divided by x squared minus x minus 6. And we want to see if there's any holes. So what we do is we factor. So in the numerator, we can factor a 3 out, and we get 3 times the quantity x minus 3. In the denominator, we can write it as two binomials, excuse me, x plus 2 times x minus 3. Now, here we have our two binomials are exactly the same. One's the numerator, one's the denominator, so they cancel each other out. So that's where we can look at this. If the original function is undefined where x equals a, this is undefined when x equals a for x minus 3. So that is undefined. If we substitute in a positive 3, 3 minus 3 is 0. This whole function would be undefined. However, because we have x minus 3 in the numerator and the denominator, they cancel out. So after we've simplified it, it is defined for x is equal to 3. Now you cancel any common terms. So that's what we did. X minus 3, those are canceled. The terms that have been canceled when set equal to 0 are the wholes. So we've only had one, x minus 3. To find the whole, we say x minus 3 equals 0, add 3 to both sides, and we get a whole at x equals 3. Now, in the denominator, we still have a vertical asymptote, and that's going to be wherever that's equal to 0. So we say x plus 2 equals 0, subtract 2 from both sides, and we get x is equal to negative 2. And we can take a look at what that graph looks like. Have it sketched out already. We can see that we have the function in blue, and we have our vertical asymptote at x equals negative 2. Now it doesn't show up on here, but we can track it, and as we go, start to increase. So we skipped it. Oh, there it was. Okay, so at 3, this function is undefined. You can see now that there's an open circle there. It's closed circle everywhere else, but when we get to that value of 3, it becomes an open circle, and that is undefined. And when you graph it, you should put an open circle in your graph anywhere that it's undefined.